Okay, so I'll just go ahead and get started. Hopefully everyone had a good Easter and good break last week. So this week we're doing Lab 8, gathering and understanding weather data. There will be a lot of stuff that we need to cover today. So I'll do the PowerPoint and then I'll explain and show you how to get the data for your chart on page 72. And then you'll fill out, we're giving you what you would have taken for orchestral measurements, and then you'll get two other weather station data, write that. And then what you'll be turning in this week is the filled out chart on page 72 and answer those two questions. And then there's 6 more questions on page 73. So you'll turn in scans of page 72 and 73. And then there's also an Excel graph that you will have to make that I'll show you how to go over as well. So I'll go ahead and start with the lecture. It's Lab 8, Gathering and Understanding Weather Data. There's 3 parts. The actual experiment part that we would have done in the lab is you would have made your own clouds with a heat plate and a match and ice. And I have a video demonstrating exactly what you would have done, so we'll watch that later. The objectives is to measure various weather parameters, explore the relationships between, I believe it's going to be relative humidity and air temperature is the one we're going to look at in our graphs, and then to make your own cloud. Why should we care about air and weather? There's the ozone hole in the Antarctic. Temperature is rising because of climate change. Land ice is melting, and that is our largest freshwater component. Sea level rise. We're not doing Lab 9 anymore, which would have gone into sea level rise more. So just make a note of that. We won't be doing Lab 9. More frequent and extreme storms is due to changing weather patterns, increased drought and floods. California's had a pretty intense drought the last couple of years. And then changing temperatures and weather also can cause species to go to extinction. Air is mostly nitrogen and oxygen, and then there's a bunch of smaller gases and water vapor in there as well. There's 3 states of water: solid, liquid, or gas. Change from liquid to gas is evaporation, gas to liquid is condensation, and solid to gas is sublimation. Evaporation occurs where water is plentiful, mostly think of rivers, oceans, creeks, ponds. The water heats up and it evaporates into a gaseous state. Condensation occurs where the relative humidity is 100% saturation, which occurs when evaporation is rapid or where the air is cooled. When air is saturated, the rate of evaporation equals condensation. So when the air is saturated, it's the exact same amount is becoming a gaseous state as is becoming a liquid. So 3 of the main ones we're going to be looking at is relative humidity, dew point, and relationships between those two. Humidity is a term used to describe the amount of water vapor that exists in a gaseous mixture of air and water vapor. It's a weird statement, but dew point, the temperature at which a given sample of air will have a relative humidity of 100%. It's the saturation temperature. That's going to be your dew point. And then relative humidity changes when temperature changes, and relative humidity falls when temperature rises. So I'm sure you've all seen this before. Warm air can hold more water than cold air. What happens to a glass of cold iced tea on a hot day? You're going to see the glass sweat because the air inside of the glass is colder than the air outside of the glass, so your natural room temperature outside air, so you have condensation that forms on the outside of the glass. The saturation point of air increases with temperature. So if you can see this graph, as you increase in temperature, your saturation point, which is just the amount of water that can be held in the air, increases. condensation. Clouds are the visible products of condensation and deposition within the atmosphere. We need a nucleus as a surface to start cloud formation and condensation. Those nucleus are called cloud condensing nuclei. And when you see the video later, we'll be using the smoke particles as our cloud condensing nuclei. So this is kind of a picture of how condensation starts. The cloud condensing nuclei in this example is going to be silver iodine or dry ice. And so in your first step, you just have your gaseous H2O, your water vapor, and then they introduce the chemical, and this is going to be cloud condensing nuclei. All the water molecules are going to be attracted to this and condense on it, and then you get your liquid H2O, and then it falls out as rain. So these are some examples of what can act as cloud condensing nuclei. Forest fire, you have smoke and ash. Volcanoes, the same thing. Wind erosion can do sand, gravel, anything that it can blow over. Sea waves, if it's real choppy, some of the spray can get in the air and act as cloud condensing nuclei. Pollen, chimney smoke, and then sulfate aerosol can all act as cloud condensing nuclei. They're usually very small. This is the size of a typical raindrop, 2 millimeters, and these are cloud droplets, and then these are their relative size. So when we're talking about these particles, they're extremely small, and you can't normally see them with the eye. Clouds are visible evidence of moisture within the atmosphere. They're classified by their appearance and their altitude above the surface. Here's a picture of all the different types of clouds. You have your cirrus or cirro, it's feathery, right there. Stratus or strato is layered. There's stratocumulus, stratus, and then cumulus is right there. Nimbo or nimbus just means rain. Fracto or fractus means broken. So let's see. If you see like a cirronimbus, that's just a feathery rain cloud. So you can add nimbus to the end, and that just tells you what kind of cloud you're looking at. What causes coastal fog in San Francisco is advection, warmer, moist air over the ocean surface, blows over a cooler land surface, and this causes it to condense. And then this just shows the temperature between solar radiation measured and air temperature on USF's campus. That is it for the slides. So now what we'll go over is, if you're on page 72 in your lab manual, you should have a chart. And so let me share this with you so you can see. So if you go to the lab 8 page, you'll see a bunch of links. The first column, you would have gone out in groups and gone out to the field in between the buildings by the church, and you would have taken, you would have used Kestrels to collect this data yourselves. And I have 2 videos real quick. Let me make sure you can hear it. And it just shows you how to put together the Kestrel meter and then how to use it as measurements. So here's the first one. If you can't hear it, just let me know.
Hello, this is a brief introduction to the Kestrel 5500 weather meter. This portable weather meter allows us to take weather readings of parameters that would normally be covered by a weather station that is in place. The parameters covered by this meter include the date, time, the direction, as it is equipped with an internal magnetic compass, wind speed, as well as other functions of wind speed, temperature, wind chill, humidity, the heat index, dew point, the wet bulb temperature, pressure, barometric pressure, altitude, and also provides summary screens of all of that data. In order to function properly in the field, this weather meter is also accompanied by a portable weather vane kit. This kit comes in 5 parts, as seen here, and allows us to build a weather vane. This vane, once assembled, rotates freely around an axis and also holds the weather meter. This can be mounted upon a monopod or a tripod and left in the field to take measurements at an elevation higher than ground level so that we can get accurate readings of wind speed. You can see that it moves freely upon the rotating axis.
Okay, so that was how to put together your Kestrel meter. If you ever do use one, just make sure that this white cap is off of the fan, otherwise you won't get any wind measurements. So here's another short video just showing you what it would look like in the field. This one's using a tripod.
Hello everyone. Today we are going to be looking at a field application for the Kestrel 5500 weather meter. Now we understand how to assemble the weather kit and the vane, and now we can see that it is properly put together and placed on a tripod in the middle of an open field. It's important that we have our setup in the middle of an open space so that we avoid as much interference as possible from nearby buildings or large trees. You can see that we are substantial distance from both the nearest building and the nearest tree. This prevents any obstructions and changes that we can see occurring in the wind speed and direction because of our obstacles. Here you can see that as the wind blows, the propeller on our meter spins and it readjusts itself to face the direction that the wind is coming from. When we are ready to take our readings, we want to make sure that we're about 2 feet or so back from the meter so that we don't interfere with the readings of the wind's velocity or the direction. Each time we want to change the parameter that we are measuring, we will just press the up and down arrows and then, of course, step back and give it a little bit of time to re-equilibrate itself so that we are making sure we're taking proper measurements. Here we have our Kestrel set to take time and date, wind direction, wind speed in meters per second, temperature in degrees Celsius, relative humidity, and our dew point temperature. We also have options to take pressure readings as well as altitude readings.
Okay, so that's what we would have done and how you would have collected the data. For the first column, it says individual Kestrel measurements, since we obviously cannot do that. If you go on the Lab 8 page, this link right here, Lab 8 Understanding Weather Data form with Kestrel data. If you open that, you'll get this page with we've given you data for the first Kestrel set. So you can just copy these measurements down in your first column, and that's the first column. So for the second and third column, you are going to go to a website called Weather Underground, and the link is on page 69, number 3. So just W Underground, and you're gonna get this website. If it brings you to like a black screen, all you have to do is right here, click on search locations, and then just type in San Francisco, and it will bring you to this web page. So this is just the current, so I'll go through each parameter that you need to find and write down, and I'll show you exactly where it is, and I'll kind of explain it. The first one, first things first, when you look at this will be your temperature. If it's probably going to be in Fahrenheit. So if it's 60, or really if it's higher than anything over 30, then you will need to change this. So what you'll do is in the top right-hand corner, you'll just click on this settings page, and then you'll just click on the Celsius, and everything will update. So going one by one from the top, time, you can just use the time on your computer, or right here, it'll tell you the time. Wind direction, and it wants it in degrees. Don't write north, northwest. So your wind direction is going to be this little dial right here. Inside it is going to be your wind speed. Don't worry about this gusts number, that's just your maximum. We want your average. So if you were filling it out right now, it would be 1, and then this black triangle is going to show you where your direction is. So instead of using the cardinal directions, we want degrees. So it's just the degrees of a circle. If you look at this, you'll just look at where this is and then do your best guess. It doesn't have to be completely accurate. It would just be somewhere around here, probably between 202 and 225. Just get a guesstimate of your best. So you've got wind direction, wind velocity is going to be this number inside. Air temperature is just going to be this one in the big circle. Use the big number, not what it feels like. Use this big number. Your relative humidity, if you scroll down, you'll find this additional conditions chart. You'll have your humidity is right here, and that's in percent, so that's good. Your dew point temperature is just going to be right above humidity. And then your altitude, if you scroll up to the top, right above where it says where you are, you'll have elevation right here, and that'll tell you the elevation of your weather station. So that'll be the second one. And then for your third one, you can do another station in San Francisco, or you can do really anywhere in the world that you want. You just need to pick a different weather station. All of these dots are different weather stations. When you're doing your second column for San Francisco, try to pick this one. It's the one closest to campus, but it's not completely important that you actually do this one as long as it's around campus. And then for your third column, you'll take the exact measurements just from anywhere else. You can do London, Rome, anywhere, the city that you're in right now if you're not in SF, just anywhere that's far enough away that you'll get different measurements. And then once you fill out that chart, you'll be able to answer question 1. So that's that part. if you have any questions on that later, need help with the website, you can just ask me, but I'll go ahead and keep going since we still have a decent amount to cover. So the next part is you'll download this Excel file, and we're going to look at the relationship in weather parameters. So you'll download this Excel file. This will come up, and it's just a giant data set. There's really good instructions on telling you what to do. It says make 2 graphs. We're only going to be making 1. Let's see what page. On page 70, at the very top, it says instructions. That's step by step on what graph you're going to make, but I'll go over it real quickly right now, just so if you want to go along with it with the video later, or if you want to try to do it now, that's fine as well. So we're going to be looking at, this is just weather data from every second of October 17th, 2010. And we're going to chart how relative humidity and air temperature are related throughout the day. So we're going to want to put that on a scatter chart. So there's something crazy like 8,000 lines. So don't try to highlight everything from the bottom. It's easiest if you just highlight A, B, and C, and that'll get every single cell. So once you have those 3 highlighted, you're going to want to go to Insert. And then down here, we're going to be doing a scatter chart. So it's this first one, just regular scatter. This will show up. You're going to want to double click on either one of these data sets, the lines, and what you're going to want to do is click secondary axis. And that's going to have another axis right here. You're going to, once again, you need axis titles. This down here is labels, but you're not going to be able to read anything, so you can just get rid of that. So this is going to be your chart. You have your relative humidity, your air temperature, and then as you move right on the graph, you get later in the day. This is just showing the relationship between them. You need your axis titles. This one maxes out at 100. This one maxes out at 20. If you look over here at the actual cells, it should be pretty easy and obvious of which one's air temperature and which one's relative humidity. So you'll just have to write those in there. And then for the chart title, you'll just have to do something descriptive like relationship between relative humidity and air temperature. Make sure when you put your axes titles that you do have these units. On your air temperature, make sure that it is written that it is in Celsius and that your relative humidity is in the weather stations. All right, let me go back real quick. So the weather stations, you just click right up here and you hit change. And then this is what the normal page looks like. If you can do find nearest station. Hold on, I can't see the chat right now for some reason. Okay. So I'll go back to the Excel sheet. So can you guys see this Excel sheet? Okay. Could you guys see it when I made the graph, or do I need to do it again? Okay. So this is all you're going to be doing for the Excel. You just need these two axes. You need to put labels on them. You need a chart title. And then down here at the bottom, yeah, I'll do it again after we go over the third part. And then just so the recording, it's already on there. But so you'll just, down here, you'll just do time. And then, so that's the second part. You don't need to answer any questions about that. So that was the second part. You'll be turning in the Excel sheet. You just have to have this chart on it. And then, so there's one last part to this lab, which is the actual experiment. So we'll be watching a video that has that on it. Let me know if you cannot hear it for some reason.
Hi, this is going to be a demonstration walkthrough of the cloud in a beaker portion of the weather lab. So first things first, you can see here that we have our hot plate / stir plate set up. We have a dry 600 milliliter beaker, and we have our magnetic stir bar sitting inside of it already. This guy. So before we turn on the heat, we'll add a couple of drops of water, and we're going to cover our system to make it into a closed system. And this is just using a little bit of aluminum foil. Okay. Go ahead and turn our stir bar on. So it should be spinning at about 600 revolutions per minute. And we'll also turn the heat on to about 100 degrees Celsius. Now, what the stir bar does is it circulates the air, and the heat will eventually evaporate the water, bring water moisture into the air. So conditions inside of our beaker should take about 10 minutes or so to stabilize. And in the meantime, one of the things that we're going to want to be aware of is how the conditions inside of this beaker should change. So we won't sit through the whole 10 minutes, but I will pause here and there and bring us back in to take a look at how the conditions have changed over time. And actually, even now we can see the beaker clouding up a little bit, so let's zoom in and see if we can take a look at that. Yeah, where the beaker was clear before, we now see a little bit of cloudiness film forming, and that's the condensation from the water vapor right alongside the inside of the beaker. And one very interesting thing to be aware of is, just get this to focus, is right here we see a line. The condensation is not formed here, but it is forming right here. It may not be quite as visible on camera, but I can see it quite clearly, and hopefully it'll become a little more distinct as our experiment rolls on. Okay, so it's been about 10 minutes or so, and the conditions inside of our beaker look like they're about stable, meaning that we don't quite see the condensation line rising very rapidly. As I lower my finger down the side of the beaker, this upper portion is relatively cool to the touch, but as I get lower and lower, there is a lot more heat. It's a lot warmer closer to the bottom of the beaker. And that makes sense, as the bottom of the beaker is close to the hot plate. So as far as conditions inside of our beaker go, we see that it is cloudy or is full of condensation near the top, and is clearer, meaning there's a lot less condensation near the bottom. Closer to the top, we have a cooler section, and at the bottom, we have a warmer section. Now, moving on to the next part of our experiment, we're going to go ahead and open up our system to add just about 50 milliliters of water to our beaker. So here, we'll pour out approximately 50 milliliters, and add that to our setup. Now I'm resealing our beaker, and what I'm going to do is put a little bit of ice on top of it. So just as we saw from the first part of our experiment, we had a temperature gradient, a temperature differential, warmer zone near the bottom and a cool zone near the top. We're going to replicate and actually emphasize that same thing here. And this mostly is for the sake of making it go a little bit faster. So we definitely have that warm spot near the hot plate. And here, with our ice, we force a cooler spot, a much colder spot in our beaker near the top. Now we're going to give this about 5 or so minutes to stabilize again, and after we do that, we'll go on to the last part of our cloud in a beaker experiment. Alright, so it's been about 5 minutes, and let's take a look at our beaker. Conditions inside should have stabilized. So we see a lot of condensation on the outside, or rather the inside of the walls of our beaker. And that makes sense as we have a lot more water, a lot more moisture inside of our system now. So, if I were to peel up our aluminum foil just to take a look at the conditions inside of the beaker, everything looks clear. Despite there being some condensation on the walls, it looks pretty clear inside. Now the next thing we're going to do is light a match. We're going to let it burn for a little bit, and then we're going to toss it inside of our beaker. Seal it up for a little while, and look at that. See a little cloud funnel tornado thing starting to appear. Now, let's pop this open. And you can see wisps of cloud coming right out. Now, if we were to let this go for, a while, right, minutes on end, then this would still occur. All of this condensation, all of this cloud will still pour out of the beaker. Now, in comparison, if we were to take another match, light it, let it burn, but then blow it out, have smoke coming off of it. And in a few seconds, the smoke stops. So, one of the questions that we'll be asking in our lab is, what is it that's coming out of the beaker? Is it smoke? Is it condensation? Is it something else? And why? So, there we have it. That is going to be a walkthrough of the cloud in a beaker portion of the weather lab.
Okay, so that was what you would have done in the lab. It's one of the cooler experiments that we would have done, but just the main takeaway from the second one is when you introduce the match into the beaker, you are giving it that cloud-conducing nuclei in the form of smoke, and it creates a positive feedback loop. So once it starts condensing, then more water vapor can start condensing on the already condensed. And that's why you have that billowing effect long after the smoke disappears. It's speeding itself as a natural reaction. And that's why it can go on for minutes while the match goes out in just a couple seconds. So if you need to watch any of those videos again, all three of them, the links are right here on the Lab 8 page. You will be using that cloud in a beaker video to answer questions 2 through 7. And so that's it for instruction. Once again, you'll just have to turn in pages 72 and 73 with the completed chart, with the data that we gave you, and then data from the 2 underground weather stations, that one's in San Francisco and the other one is of your choosing. Just make sure on that line that wherever you choose, make sure that you let me know which station you use. It doesn't have to be the lab number or anything, but if you chose Sydney, Australia, just write Sydney, Australia or something like that. Just the city is fine enough, and then you'll answer questions on page 73, and you will turn in the Excel graph sheet. So